Nucleophilic substitution reactions of alkyl halides. Alkyl halides undergo nucleophilic substitution reaction in which nucleophile replaces halogen atom to give the product. Halogen atom is replaced in the form of halide ion. Nucleophiles will follow SN1 reaction path to give products, or nucleophiles may follow SN2 reaction path to give products. I repeat, nucleophiles will follow SN1 reaction path mechanism to give the products, or nucleophile may follow SN2 reaction mechanism path to give the product. What is SN1 reaction mechanism path? That is nucleophilic substitution unimolecular mechanism path, or nucleophile may follow nucleophilic substitution bimolecular reaction path to give the product. The question arises, when does the nucleophile will follow SN1 reaction mechanism path to give the product, and when does the nucleophile will follow SN2 reaction mechanism path to give the product? The answer for this question is when the halogen bonded carbon is attached to bulky groups like CH3, as in case of tertiary butyl halide, the halogen bonded carbon is attached to bulky groups, then the nucleophile will follow SN1 reaction mechanism path. I repeat, when the bulky groups are present on the carbon atom, the nucleophile will follow SN1 reaction mechanism path. When the halogen bonded carbon atom has small groups like hydrogen, as in case of methyl halide, then the nucleophile will follow SN2 reaction mechanism path. How to remember, when bulky groups are present, then the nucleophile will follow SN1 reaction mechanism path, and when small groups are present on the carbon, the nucleophile will proceed through SN2 reaction mechanism path. The next question arises, why does the nucleophile follow SN1 reaction mechanism path when the bulky groups are present on the carbon atom? I give you the answer. When bulky groups are present on carbon atom, the nucleophile will follow SN1 reaction mechanism path. The reason for this question is, you know that the carbon and halogen bond is polar in nature. Halogen is partially negative and carbon atom is partially positive. When the nucleophile tries to come from this side, when nucleophile tries to come from this side, the partially negative halogen atom and nucleophile, they repel each other. So nucleophile cannot attack from this end to this positively charged carbon atom. If the nucleophile tries to attack on this positively charged carbon atom from other sides, these bulky groups, they cover the carbon atom. They do not allow this nucleophile to attack on this positively charged carbon atom. As a result, nucleophile cannot attack directly to this positively charged carbon atom when bulkier groups are present on the carbon atom. Therefore, nucleophile waits for proper time. Nucleophile waits for proper situation. Nucleophile waits until the favorable condition take place in this alkyl halide. Nucleophile waits until the formation of carbocation, which is a favorable condition for nucleophile to attack on the positively charged carbon atom. Then what is carbocation? How this carbocation is formed, and why the carbocation is formed when the bulky groups are present on the carbon atom? The answer is, when the bulky groups are present on the carbon atom, these bulky groups, they face the steric hindrance. They fight for the space. They struggle for the space. They feel uncomfort. Therefore, they try to push and kick out this bromine atom. As a result, the carbon and bromine bond, it breaks unsymmetrically, that is, heterolytic breaking of carbon and halogen atom take place. As a result, we get carbocation. The bromine atom takes both the bonded electrons and it forms bromide ion, and the carbon atom has lost its bonded electron. As a result, carbon atom becomes electron deficient, so it becomes positively charged. This is called as carbocation. Carbocation has sp2 hybridized carbon atom. As you know, when carbon atom is bonded to 3 sigma bonds, it is called as sp2 hybridized. In one of my video, I have explained how to detect the hybridization in the carbon atom. When the carbon atom is bonded to 4 sigma bonds, we call it as sp3 hybridized carbon. When the carbon atom is bonded to 3 sigma bonds, it is called as sp2 hybridized carbon atom. And when the carbon atom is bonded to 2 sigma bonds, we call it as sp hybridized carbon atom. What is the geometry of this sp2 hybridized carbon atom? As you see, it is planar. It is planar. And what is the geometry of sp2 hybridized carbocation? That is trigonal. These are the important things we have to remember related to carbocation. Carbocation has sp2 hybridized carbon atom and its geometry is planar trigonal, and the bond angle is 120. The formation of carbocation takes place very slowly. This decides the rate of the reaction, therefore it is called as rate determining step. Rate determining step, RDS. So when the bulkier groups are present on the carbon atom, the first step is formation of carbocation. And when the carbocation is formed in the first step, the next step is attack of nucleophile on carbocation. The nucleophile may attack from the front side of the board. The nucleophile can attack from the front side of the board, or it may attack from the back side of the board to this carbocation. Therefore, there are two possibilities. Nucleophile may attack from front side, or nucleophile may attack from the back side. As a result, in SN1 reaction mechanism, we get two types of products. Two types of products. Two types of products. The nucleophile may attack from front side or from the back side. There are 50-50 possibilities. Therefore, in SN1 reaction mechanism, we get 50% retention product and we get 50% inversion product. Inversion product. What is retention? Retention means, if you see this tertiary butyl bromide, here the halogen atom is right side. If the nucleophile, say if I take hydroxyl ion as a nucleophile, if nucleophile is present on right side, that is at the position of bromine, exactly if the nucleophile is present on the position of bromine, then it is called as retention configuration. If the nucleophile is present at right side, it is called as retention configuration product, and if the nucleophile is present at left side, it is called as inversion configuration product. Therefore, in SN1 reaction, we get the mixture of 50% retention and 50% inversion configured products. As a result, the product is optically inactive. The product does not show optical activity. What is optical activity? That we are going to study in detail in next video. In this video, we are going to learn in detail SN1 and SN2 reactions and all types of multiple choice questions, JEE and NEET level questions we are going to solve in this video. In making of this video, I have taken lot of efforts. So I request you, please like, share and subscribe my channel. And I'm your friend Avin. As we have seen that SN1 reaction take place when the bulkier groups are present on the carbon atom. Now we will see the SN1 reaction reactivity order. The SN1 reaction reactivity order, this is most important, reactivity order. The benzyl halide undergoes, benzyl halide means when the halogen atom is attached to carbon atom next to benzene, it is called as benzyl halide. Benzyl halide, it undergoes very fast SN1 reaction, then comes allyl halide. Allyl halide. Allyl halide means when the halogen atom is attached to carbon atom next to carbon-carbon double bond, it is called as the allyl halide. Then the tertiary alkyl halides, then secondary alkyl halides, then primary alkyl halides or 0 degree alkyl halides. 0 degree alkyl halides. You have to remember here that the S reaction takes place very fastly, readily in benzyl halides, then allyl halides, then tertiary alkyl halides, and the secondary alkyl halides, they may or may not undergo SN1 reaction mechanism because it depends upon the reaction conditions. And the first degree and 0 degree alkyl halides, they do not undergo SN1 reaction mechanism, they undergo SN2 reactions. So this is the SN1 reactivity order: benzyl, allyl, tertiary, secondary, primary and 0 degree alkyl halides. Formation of carbocation is favored by polar protic solvents. As a result, SN1 reaction is favored by polar protic solvents. What are solvents? What are polar protic solvents? And what are polar aprotic solvents? Let us see. Solvents are classified into two types: polar solvents and non-polar solvents. Polar solvents have positive and negative ends or positive and negative poles within the molecules, and non-polar solvents, they do not have polarity. Examples of non-polar solvents are cyclohexane, benzene and normal hexane, normal hexane. These are the few examples of non-polar solvents. Now, polar solvents, they are further classified into two types. The first one is polar protic solvent, polar protic solvent, and second one is polar aprotic solvent. Polar protic solvents, they have positive and negative pole within the molecule and they can produce H plus ions. For example, water is a polar protic solvent. It produces H plus ion in the solution, H plus OH minus. Another example of polar protic solvent is alcohol. For example, CH3OH. It can also produce H plus ions. One more example of polar protic solvent is acetic acid, CH3COOH. It has H plus and CH3COO minus. This acetic acid is also polar protic solvent. It produces protons, that is H plus ions. And polar aprotic solvents, they have polarity but they cannot produce H plus ions. For example, acetone, CH3. This has negatively charged oxygen and this end is positive, but it cannot produce H plus ions. So this is polar but aprotic solvent. Immediately we have to guess that when polar protic solvent is used in the reaction, then that reaction follows SN1 mechanism. And when the polar aprotic solvent is used in the reaction, that reaction must follow SN2 reaction mechanism. So these are the hints, these are the tricks we should remember. Polar protic solvent, SN1 reaction. Polar aprotic solvent, SN2 reaction. We should know the list of polar aprotic solvent. That helps us to guess the reaction is SN2 reaction. Now we will take the list of polar aprotic solvents. We will take the list of polar aprotic solvent. The first example is acetone. We have to remember the structure of acetone so that we can write very easily other polar protic solvents. Now just change here, instead of carbon you write sulfur, that is CS3, S double bond O, CS3. It is called as dimethyl sulfoxide and it is well known as DMSO. Dimethyl sulfoxide. Another example of polar aprotic solvent is, this is aldehyde group, this is dimethyl formamide, DMF. Dimethyl formamide, DMF. One more example we will take, CS3N, CS3, CO, CS3. This is called as dimethyl acetamide, DMA. This is called dimethyl acetamide. So these are the polar aprotic solvents. Whenever you come across polar aprotic solvents in the reaction such as acetone, DMSO, DMF, DMA, you have to decide that the reaction is SN2 reaction. Now we will take two questions, whether the reactions follow SN1 or SN2 mechanism. If we see the first question, here alkyl halide is given and nucleophile, and here the solvent is acetic acid is given. Here we don't know whether the bulkier groups are present on the carbon atom or not. So we cannot decide from this alkyl halide whether it will follow SN1 or SN2. But if you see here, the solvent used is polar protic solvent. Therefore polar protic solvents, they favor SN1 reaction. So the first reaction follows SN1 reaction mechanism. Now let us see the second question. Here also alkyl halide is given, but which alkyl halide we don't know, whether there are bulkier groups or whether there are small groups are present on the carbon atom, we don't know. So we cannot decide whether the reaction will follow SN1 or SN2 from the alkyl halides. But the solvent is given. Here the solvent is polar aprotic solvent. Therefore it clearly indicates that the polar aprotic solvents, they favor SN2 reaction. So the second reaction follows SN2 reaction mechanism. Now we will see the SN1 reaction super tips. The first tip is bulkier groups favors SN1 reaction. That is, when bulkier groups such as benzyl halides or allyl halides or tertiary halides present, then the reaction will follow SN1 reaction mechanism path. Second, SN1 reaction take place in two steps. In first step, the formation of carbocation take place. I have already explained why the formation of carbocation take place. The answer is the bulkier groups present on the carbon atom, they feel uncomfort, they fight for the space. Due to steric hindrance, they feel uncomfort. As a result, they push the halogen atom. The carbon and halogen bond breaks unsymmetrically, heterolytic fission takes place, and halogen atom takes both the bonded electron and it leaves the molecule in the form of halide ion, and the carbon atom becomes electron deficient because the bonded electron is taken by the halogen atom and the carbon atom has lost its electron. As a result, carbon becomes electron deficient center and it is called as carbocation. Carbocations are also called as carbonium ions. Second step is the attack of nucleophile on the carbocation. As a result, SN1 reaction take place in two steps. The first step is slow step. It take place very slowly. The formation of carbocation take place very slowly. As a result, the first step is the rate deciding step. Therefore, it is called as rate determining step, RDS. The next point is the SN1 reaction is unimolecular reaction because the rate of the reaction, rate means the formation of the product, depends upon the number of carbocations. If 1000 tertiary butyl bromide are used, 1000 carbocations are formed. As a result, we get 1000 products. If we use 2000 tertiary butyl bromide, we get 2000 carbocations and we get 2000 product. That means the concentration of the alkyl halide is increased, the product is also increasing. As a result, the rate of the reaction depends upon the concentration of alkyl halide only, that is tertiary butyl bromide only. Therefore, the SN1 reaction are called as unimolecular reactions and they follow first order reaction. Then SN1 reactions, they are favored by polar protic solvents, and in SN1 reaction 50% retention configuration product and 50% inversion configuration products are obtained. The net result of the product is, it is racemic mixture. It is optically inactive. These are the very important points related to SN1 reactions. Now, with these important tips, we are going to solve JEE and NEET related questions. Here we go. Before we discuss multiple choice questions, we will take super tricks for SN2 reaction. Alkyl halides with small groups undergoes SN2 reaction. For example, alkyl halide like methyl bromide. This methyl bromide, here the carbon atom has small groups or small atoms. When alkyl halides having small groups are reacted with nucleophile, say OH minus. Here, as we know that the carbon and halogen bond is polar in nature, carbon is partially positive and bromine is partially negative. The nucleophile has lot of space, lot of open space here. So nucleophile can attack to this positively charged carbon atom from back side very easily. Nucleophile will not come from front side because here already bromine, which is negatively charged, and nucleophile is also negatively charged. If the nucleophile comes from front side, there is repulsion between the halogen atom and the nucleophile because the like charges repel each other. As a result, this nucleophile, it attacks the carbon atom from backside. So we get a transition state like this. Here the nucleophile has attacked on the carbon. Here the nucleophile OH minus has attacked on the carbon atom and it tries to form the bond. At the same time, the carbon and halogen bond, it gets weakened. This is called as transition state. This is called as transition state. If you see this transition state, it is highly unstable. The reason is carbon atom is bonded to 5 bonds. 1, 2, 3, 4, 5. Carbon cannot be pentavalent. Therefore, carbon tries to come into tetravalency. As a result, it breaks one bond, that is the bond between carbon and halogen atom finally breaks and we get the product like this. We get methyl alcohol and bromide ion. And if you see the reaction, the SN2 reaction is taking place in a single step, that is attack of the nucleophile and breaking of the carbon and halogen bond take place simultaneously, and in one step we get the product. Therefore, SN2 reaction take place in a single step. In SN1 reaction, we have seen there was the formation of carbocation. In second step, there was attack of nucleophile. Therefore, SN1 reaction was taking place in two steps, but SN2 reaction take place in a single step. In SN2 reaction, there is transition state. What is transition state? It is highly unstable state in which the carbon atom is pentavalent. If you see the product is 100% inverted. In SN2 reaction, we get 100% inverted configuration product. Why we call it as an inverted product? If you see in the methyl bromide, the nucleophile bromine is present at right side, and if you see the product, the nucleophile OH is present at left side. Therefore, it is inversion. The polar aprotic solvents like acetone, DMS, and DMF and DMA, they favor the SN2 reaction. Now we will see the SN2 reactivity order. The 0 degree halides like methyl halide, this is 0 degree halide. 0 degree halide, they undergo very rapidly SN2 reaction, then primary halides, then secondary halides, then tertiary halides, then allyl, then benzyl. 0 degree alkyl halides, they undergo very rapidly, that means immediately they undergo SN2 reaction, then primary, then secondary, tertiary, allyl and benzyl. And you have to remember that as we go from the primary, secondary, tertiary, the SN2 reactivity decreases. That means the tertiary to allyl and benzyl halides, they negligibly undergo SN2 reactions. In other words, I can say tertiary, allyl and benzyl, they do not undergo SN2 reactions. And what about secondary alkyl halide? Secondary alkyl halide, they can undergo either SN2 or SN1. It depends upon the reaction conditions that we are going to see later. Now we will see top MCQs. The first question is, which one would go SN2 reaction between these two? We know that SN2 reaction order is the primary alkyl halides, they undergo very fast, then secondary, then tertiary, then allyl, then benzyl, like this. And if you see in this molecule, the halogen atom is attached to the carbon, that carbon is attached to one more carbon. That means this compound is the primary alkyl halide. And if you see here, the halogen atom is attached to this carbon is attached to two other carbon atoms. Therefore, this is secondary alkyl halide. Therefore, SN2 reaction is favorable in primary alkyl halide. Therefore, this molecule will undergo SN2 reaction. This would go SN2 reaction. And if they ask what is the order of SN2 reaction in between these two, then you have to show that this molecule will go easily or readily SN2 reaction than this. Now, the second question, what is the order of SN2 reaction in these molecules? If you observe all these four molecules, they are primary alkyl halides because the halogen atom is attached to the carbon, that carbon is attached to one more halogen atom. Therefore, this is primary, this is also primary, all are primary alkyl halides. Then, how to decide the order of SN2 reactivity? The hint for this is when the alkyl groups are same, then we have to compare the size of the halogen atoms. Bigger the size, easy leaving group. Bigger is easy leaving group. Therefore, iodine is bigger, so it is easy leaving group. Therefore, it undergoes SN2 reaction very rapidly. Therefore, the first is iodobutane. Then the next molecule, bromine, that is third. Then chlorine, that is 4. Then fluorine, fluorobutane or butyl fluoride. This is the SN2 reactivity order. Let us consider one more very important question, and most of the students, they make mistake in this question. What is asked? We have to arrange in the decreasing order of SN1 reactivity for these molecules, and we know that SN1 reaction take place by the formation of carbocation. Let us consider the carbocations of these molecules. If this molecule form a carbocation, means this carbon and halogen bond breaks, this carbon becomes carbocation, means it becomes like this. This is the carbocation of this molecule. Now the carbocation of this molecule is and the carbocation of this molecule is, and if we see the carbocation of this molecule, this is primary carbocation, and this carbocation is resonance stabilized. Therefore, this carbocation is more stable. Therefore, the second structure will go SN1 reaction very rapidly. And if you consider between this and this is vinyl carbocation, vinyl carbocation, and we should remember that vinyl carbocations, they least undergo SN1 as well as SN2 reactions. So vinyl carbocations, they get last priority. Therefore, the third and then the first. This is the SN1 reactivity order for these three molecules. Second structure, then first structure, then vinyl, third structure. And if we are asked arrange the SN2 reactivity order in these molecules, then we have to think in different way. If you see here, the double bond is on beta carbon atom, that is, this is alpha carbon atom and this is beta carbon atom. And if you see here, the double bond is on, this is alpha, this is beta, and this is gamma. If you see here, the double bond is on gamma carbon atom, and here the double bond is on beta carbon atom. As the double bond is close to the carbon bonded to the halogen, SN2 reactivity will be more due to minus I effect. Therefore, the second structure will undergo SN2 reaction rapidly, and between these two structures, as you see here, the bonded electron, they undergo resonance, and due to resonance, there is a double bond character between the carbon and the halogen. As you see here, due to resonance, there is a double bond character between carbon and halogen halogen atom becomes difficult leaving group, so it has least priority. We have to remember that vinyl halides, they undergo very less SN1 and SN2 reactions. They occupy the least position than the first. So in these molecules, the SN1 reactivity as well as SN2 reactivity will be of the order 2, 1, 3. Therefore, in this question, the SN1 as well as SN2 reactivity order is 2, 1, 3. Let us consider one more question. Arrange in decreasing order of SN1 reactivity in these molecules. We know that SN1 reaction take place due to formation of carbocation, and we have to remember that the stability of carbocation increases by electron donating groups due to plus I effect. So here the carbocation is formed on carbon atom, and this carbocation stability increases due to presence of electron donating groups. Therefore, we have to find out which groups are electron donating group. Here methoxy group is powerful electron donating group, and NO2 is electron withdrawing group, CN is neutral, and CS3 is again electron donating groups. Therefore, between these first and fourth, between these two electron donating group, methoxy group is more powerful electron donating, that it has more plus I effect, therefore it stabilizes carbocation, therefore the first structure undergoes SN1 reaction rapidly. Then fourth one, and as you see, NO2 is powerful electron withdrawing group. Due to minus I effect, it destabilizes carbocation, therefore it undergoes SN1 reaction least, means it will come at the end, that is, then comes third. So this is the order of reactivity for SN1 in these molecules. Now we will take very interesting question, that is, write the SN1 and SN2 reactivity order in 4-isomeric bromobutane. First we have to write the 4 isomers of bromobutane. We can write the isomers of bromobutane. First we have to write all 4 carbon atoms in a straight chain, then we have to attach bromine. I do not write hydrogen atoms here in order to save the time. The second isomer of bromobutane is, I have to reduce 1 carbon atom in the chain and we have to make 1 carbon chain. This is second isomer of bromobutane. Then the third is, I write all 4 carbon atoms in the straight chain, then I write bromine atom on the second carbon atom. Then last possibility is 2 branches on the carbon atom, and this is the bromine. So these are the 4 isomers of bromine. I give the number for these 1, 2, 3 and 4. And first let us write the SN1 reactivity order. And we know that SN1 reaction take place when there are bulkier groups on the carbon atom, that is more branches. That means this is tertiary alkyl halide. Therefore, this will undergo the reaction, SN1 reaction, very rapidly. Therefore, SN1 reactivity order is, the fourth will go SN1 reaction very fast. Then this molecule, the halogen is attached to the secondary carbon. So it comes second. Then this carbon atom, in this molecule there are more branches. Then lastly the primary alkyl halide. Therefore this is the SN1 reactivity order, that is tertiary, secondary with more branches and normal alkyl halide. This is the order of reactivity of SN1. Then SN2 reactivity order is exactly opposite. The first, then second, then secondary, then tertiary. This is the order of SN2 reactivity. The next question is, write SN1 and SN2 reactivity order for these molecules. And we should know that the SN1 reactivity is tertiary, secondary and primary. This is SN1. And SN2 reactivity order is exactly opposite, 1 degree, 2 degree and 3 degree. Let us find the degree of these molecules. The bromine is attached to carbon. This carbon is attached to one more carbon. That means it is primary. And here the bromine is attached to the carbon. That carbon is attached to 2 other carbon. Therefore this is secondary. And in this molecule the bromine is attached to the carbon. That carbon is again attached to 2 other carbon. Therefore this is also secondary. And the last one is, here halogen atom is attached to the carbon. That carbon is attached to 1, 2, 3. Therefore this is tertiary. Therefore SN1 reactivity order is tertiary. Tertiary means this is the fourth. It undergoes very rapidly or very easily SN1 reaction. Then the secondary alkyl halides, there are 2 secondary alkyl halides, and one factor we have to apply, that bulkier groups, they favor the SN1 reaction Therefore, in these two secondary molecule, this has more bulkier groups than this molecule. Here one benzene ring is there and one methyl, but here there are two benzene rings are there. Therefore, this secondary alkyl halide has bulkier groups than this molecule. Therefore, second number is 2, then the third, then the primary alkyl halide, the first. And the SN2 reactivity order is exactly opposite of this. The primary, that is first, then between secondary, this has smaller group than this, therefore third number comes, then comes the second, then comes the tertiary. Therefore, this is the order of SN1 and SN2 for these molecules. Now let us take one more example, that is write the SN2 reactivity order of these molecules. Here the halogen atom is same, and if we write the structure of each molecule, all these molecules are primary alkyl halides. That means all will undergo SN2 reaction, and we have to decide which will undergo SN2 reaction very fast. That can be decided on the length of the carbon chain. Smaller the carbon chain, more will be the SN2 reactivity, and as the carbon chain increases, SN2 reactivity decreases. Therefore, the order in this case is this will undergo SN2 reaction first, then this. So this is the answer. In this question, SN1 reaction occurs through formation of option 1 carbocation, carbanion, free radical and transition. And we have already seen that SN1 reaction, it take place in carbon having bulkier groups, and the nucleophile cannot attack on the carbon carrying positive charge. So due to presence of bulkier groups, therefore nucleophile waits until the formation of carbocation. So the SN1 reaction occurs through formation of carbocation. This is the correct answer. And what is the carbanion? Carbanion means carbon carrying the negative charge. And what is free radical? The species which carries odd number of electron is known as free radical. And what is transition? When the carbon atom is pentavalent, which is unstable, that take place in SN2 reaction. So SN1 reaction occurs through formation of carbocation and not by the formation of carbanion or free radical or transition state. The next question is, arrange in decreasing order of SN1 reactivity in these molecules. And we know that SN1 reactivity order is benzyl, then allyl, then tertiary, secondary and primary. Let us check out these molecules. This is primary alkyl halide, and here this halogen atom is attached to two other carbon atom, but the halogen atom is attached to this carbon, that carbon is attached to doubly bonded carbon atom, therefore this is allylic halide, and this is secondary alkyl halide. So we know the order, that is allyl halides, they undergo SN1 reaction rapidly. So second will go SN1 very rapidly, then third, then first. This is the order of reactivity towards SN1 reaction. The next question, the rate of SN2 reaction is maximum when the solvent is. We know that SN2 reactions are favored by polar aprotic solvents. Means the solvent must be polar, but it should not release the H plus ion. We have to find which is the polar aprotic solvent. Let us consider methyl alcohol. Methyl alcohol means CH3OH. Here H plus is available. Therefore, this is polar protic solvent. So water is HOH. Here H plus is also available. Therefore, water is polar protic solvent. It is not favorable for SN2 reaction. and dimethyl sulfoxide is polar aprotic solvent, that is dimethyl sulfoxide is polar aprotic solvent that favors the SN2 reaction, and benzene is non-polar solvent, so it is not favorable for either SN1 or SN2 reaction, so it is out of contest. Therefore, out of these four solvents, dimethyl sulfoxide is polar aprotic solvent that favors the SN2 reaction. Therefore, the answer is 3. In this reaction, we have to decide SN2 reactivity order, and we know that decreasing order of SN2 reactivity is primary, secondary, tertiary. And here let us check out this alkyl halide. This is primary alkyl halide. Here also this is also primary alkyl halide. Here also primary alkyl halide, and this is secondary alkyl halide. And we know that primary alkyl halides undergo SN2 reactivity very easily, but here we have 3 primary alkyl halides. Then how to decide that? One thing we have to remember that when primary alkyl halides are there, and electron withdrawing groups are present, oxygen is electronegative, it withdraws the electron, therefore it favors the SN2 reaction. Therefore, the reactivity order of electron withdrawing group in this, it comes first, so second will undergo very rapidly SN2 reaction. Then in these two, that is the methyl chloride and the ethyl chloride, and I have already told you that as the chain increases, SN2 reactivity decreases. So between these two, this has small chain, therefore this will undergo SN2 reaction very rapidly. Then comes this, then lastly secondary alkyl halide. Therefore this is the order of reactivity towards SN2 reaction. Once again I will tell you that electron withdrawing groups, it favors SN2 reaction. Now let us take one more question, SN1 reactivity order in these molecules. We know that SN1 reactivity order is tertiary, secondary, primary. Okay, we have to decide these molecules, they are primary, secondary or tertiary first. And one more thing we have to remember here, we have a bridged molecule, and you have to remember that when the bridged molecules are present, there is a bridge atom between these two carbon atoms. Such molecules, they have least priority even in SN1 and SN2 reaction. So we have to keep them the least reactivity in the SN1 as well as in SN2 reactions. So let us see this molecule. This molecule is primary alkyl halide because the halogen atom is attached to this carbon is attached to one more carbon. Therefore, this is primary alkyl halide. Here if you see this halogen atom, it is attached to 1, 2, 3. That is, this halogen atom attached to this carbon is a tertiary carbon atom. Therefore, this is tertiary alkyl halide, and this carbon is secondary. Therefore, this is secondary alkyl halide, and this is bridge molecule. Therefore, the tertiary alkyl halides, they undergo rapidly the SN1 reaction. Therefore, the second molecule is tertiary, then secondary is the third molecule, then the primary is first molecule, and bridged molecule, they have least priority, so we keep it at the end. Therefore, this is the order for SN1 reactivity in these molecules. The next question is SN1 reactivity order in these molecules. This question seems to be very complicated, but this question is very easy. We have to apply the SN1 reactivity order, that is tertiary, secondary, primary. So we have to find out the order of this molecule. So let us consider this molecule. Here halogen atom is attached to this carbon atom is attached to 1, 2, 3. Therefore, this is tertiary carbon atom. And if you see here, this carbon atom is secondary, so this is secondary alkyl halide. And here if you consider the halogen atom is attached to the bridge carbon atom, so it has least priority. We should not consider it. We have to keep this molecule at the end. It will not either undergo SN1 or SN2. So it has least priority. And if you consider this molecule, here the halogen atom is attached to this carbon and that carbon is attached to one more. Therefore, this is primary alkyl halide. Therefore, what is the order? The order is tertiary alkyl halide means the first molecule, secondary alkyl halide means second molecule, and the fourth one, and the bridged carbon atom, it has least priority, so we keep it at end. Therefore, the SN1 reactivity order in this molecule is 1, 2, 4 and 3. The next question is, write SN1 and SN2 reactivity order in these molecules. If you consider these molecules, this is also primary, this is also primary alkyl halide, and this is also primary alkyl halide. Even though we have to write SN1 reactivity order as well as SN2 reactivity order. So in such cases, we have to apply one rule. Here halogen atom is attached to the carbon atom. The carbon atom to which halogen atom is attached, it is called as alpha carbon atom, and next carbon is beta carbon atom. Here on the beta carbon atom, here this is alpha carbon atom and this is beta carbon atom. This is alpha carbon atom and this is beta carbon atom. And as the number of branching on the beta carbon atom increases, if you see in this molecule on beta carbon atom there are two branches. If you see here on beta carbon atom there is one branch. If you see here on beta carbon atom there is no branch. Therefore, the SN1 reactivity order increases as the branching on beta carbon atom increases. Therefore, here more branches are there in beta carbon atom. Therefore, it undergoes SN1 reaction rapidly, then second molecule, and here no branching. Therefore, this is the order of SN1 reactivity order. And for SN2 reactivity order, as branching increases, SN2 reactivity decreases. Therefore, this molecule 1 has less branching, therefore it undergoes SN2 reaction very rapidly, then second, then third. As the third has more branching, so it will not undergo SN2 reaction fast. So the reactivity order is 1, 2, 3 for SN2, and for SN1 3, 2, 1. Once again I repeat, as the beta branching increases, SN1 reactivity increases, and in case of SN2 reactivity, as the beta branching increases, SN2 reactivity decreases. The next question is, write SN2 reactivity order in these molecules. If you consider all these molecules, they are all primary alkyl halides. Then it becomes very difficult how to decide the SN2 reactivity order because all are primary alkyl halides. We have to consider in such cases the percentage of S character. If you consider in this molecule, the carbon atoms all are sp3 hybridized, and if you consider here one sp2 hybrid carbon atom is there, and if you consider in this molecule there is sp hybridized carbon atom is there. Therefore, if you consider the percentage of S character, that is here in sp3 hybridized carbon atom there are totally 4 atomic orbitals are there. Therefore, if we divide it by 4, we get 25% of S character. And if you consider sp2 hybridized carbon atom, there are 3 atomic orbitals are there, 1s and 2p. If you divide it by 3, you will get 33% of S character. And if you consider here sp hybridized carbon atom, if you divide by 2, you will get 50% of S character. As the S character increases, SN2 reactivity also increases. Therefore, SN2 reactivity order is third, then second, then first. Students, I would like to give you one more very important point, that SN1 reaction is favored by weak nucleophiles like OH-, and SN2 reaction is favored by the strong nucleophiles such as SH-, CN-, and iodine-. One more point you have to remember here is SN2 reaction it is bimolecular reaction. The rate of the reaction depends upon the concentration of the both the reactants, that is alkyl halide as well as concentration of the nucleophile. And the SN2 reaction is bimolecular second order reaction. SN1 reaction is unimolecular first order reaction. SN1 reaction take place in 2 steps and SN2 reaction take place in 1 step. In this video, we have discussed about SN1 and SN2 reactions and multiple choice questions related to SN1 and SN2 reactions. This is Avin. Please like and share the video and subscribe my channel. I'm thankful to YouTube and millions of YouTube viewers.